All right, hello class. Today we're going to be going over some of your homework problems. So we have a disk at rest experiences a constant angular acceleration for time t. At the end, it is spinning with a frequency of with of a it just has a frequency. Please answer the following questions. Write an expression for the magnitude of angular velocity in terms of uh, after the acceleration terms of frequency. This is literally just omega is equal to 2 pi f. This is just one of your basic formulas. There's not any trick to this. And so then it wants you to go ahead and calculate that. So then you just plug your answer in there. And note that you have to account for your units. So go ahead and make sure that you have your right units right. And so then next up, it says write an expression for the average acceleration of the disk in terms of the angular velocity. So in this case, you just have to say that A average is going to be equal to d omega over delta t, or delta omega over delta t. And so then in this case, your time is equal to 0. T1 is going to be equal to 0. So then you'll have delta omega over t, and then we can decompress delta omega, and we can know that it's also at rest, so we can say that omega I is equal to 0. So then you just have omega f over t. And then you have to just plug your numbers in from there, and you'll be perfectly fine. So write an expression of t in terms of the frequency. From before, we had that t was equal to, I believe it was 2 pi over omega. I believe that's what we had, because we had 2 pi distance over omega, but in this case, we're going to have that this is just going to be 1 over f. Since it's in terms of frequency, frequency is already in inverse seconds, so then it makes sense that this is the formula here. And so then you just have to make sure that you get your units right here. Okay, so next up we have an ultra centrifuge. Accelerates from rest to some large number of RPMs in just under 2 minutes. And so we have to find what's the angular acceleration. From last question, we know that omega is going to be equal to 2 pi f. And from before, we also know that alpha is going to be equal to delta omega over delta t. And we apply the same relationship that we did before. And we know that it's from rest, so we know that omega I is going to be equal to 0. And so then this is just going to yield 2 pi f over t, and that should yield your angular acceleration in this case, because f is our frequency that is given here in rotations per minute, and we have our time, which is given in minutes. And so this is going to be in minutes, so you have to remember to convert this to seconds. Okay, part B, what is the tangential acceleration of a point 9 or some centimeters away from the axis of rotation? You just have to remember in this case that that AT is going to be equal to alpha R, or R alpha, however you want to put it. And in this case, R is going to be equal to L. And then you just have to plug in that, and then plug in your answer from the last one, and we're going to get that this is 2 pi f L over t. what is this? Centripetal acceleration in multiples of g. So now in this case, you have to take a and divide it by g, and that will give you your new answer. And so then you should be able to figure out what this is. Okay, so next up we have a semi-trailer truck with an odometer in it, and so we are given that the wheel has a diameter. So we know diameter of the wheel is equal to some number, and then it goes through a lot of rotations. So then we have to we ask ourselves how many kilometers should the odometer read, and so in this case we know that the circumference is going to be equal to 2 pi r, but diameter of a wheel is just going to be equal to 2r. So we can say that the circumference then is just equal to pi times d. And from there, you just have to go ahead and you have to try to find this is just for one rotation, right? So you just have to take the circumference of that wheel and multiply it by how many rotations it has, and that will give you your answer. So you just have to take c times the number of rotations, or you could put this as theta, I guess, and then this is just going to be equal to pi d times theta, which is the number of rotations. Or I guess they use it as an r here, and so it's just pi rd. And this should be your distance that you travel. Okay, so next up we have a stone in a sling is swung in a circle of radius r with a constant angular velocity of omega. Please answer the following questions. Write an expression of magnitude of the linear velocity v of the stone. You're just using, this is super basic. You're just using your formulas that we outlined in the video that you guys probably have just watched. And then b is you just have to calculate the magnitude of that linear velocity, and so then you just use the two variables and multiply them together. And then next up is part C, write an expression, the magnitude of the centripetal acceleration. I've covered all these in the video. This is super basic. And so it asks which of the following changes to the system would result in a larger centripetal acceleration. And so you just have to go ahead and you have to determine what relationships would increase the centripetal acceleration. Okay, so then if we move on to problem 5, a disk of initial angular velocity omega naught experiences a constant angular acceleration of alpha for a time period t. Please answer the following questions. Write an expression. These are just using all your kinematic equations. Yeah, just use your rotational kinematic equations to solve these problems. Okay, so a gyroscope slows from an initial rate of 28 radians per second at an angular acceleration of 0.54. It says how long does it take to come to rest in seconds? And so it says it's slowing, and it gives you the initial rate, so that means that acceleration is going to be negative. And so what we do is we take our one kinematic equation that says omega is equal to omega naught plus alpha t, and it's asking how long does it take to come to rest, which means that this is now going to be 0, and then you have omega naught plus alpha t. And so then you just solve this for t, so then t is going to be equal to negative omega naught over alpha. And this makes sense because alpha is also going to be negative, so these two negatives are going to cancel out to give you a positive time value. And so then it asks how many revolutions it takes until it stops. And so you use your other kinematic equation here, where omega squared is equal to omega naught squared plus 2 alpha theta. And so then you just solve this question for theta. And again, we're asking that this is, or we're saying this is coming to rest. So then we have negative 2 omega naught equals 2 alpha theta. And then theta is equal to negative omega naught squared over 2 alpha. And that should have it because your alpha is going to be negative. So this is going to give you a positive answer, and this should yield it. Okay, so we have a problem with some big numbers here. Okay, so next up we have an Earth spins on its axis and also orbits the Sun. For this problem, using the following constants: mass of the Earth, radius of the Earth, distance of the Earth from the Sun. Calculate the rotational kinetic energy of the Earth due to the rotation about its axis in joules. And so we take our equation for kinetic energy, and we have K is equal to 1/2 I omega squared. And we have to take what I is. And so I, for a solid sphere, we're just going to grab this equation from your book, is going to be 2/5 mr squared, where r is going to be the radius of the Earth, and m is going to be the mass of the Earth. So this is an easily calculatable number here. And so what we can do is we can plug this in and say that this is going to be equal to K is equal to 1/2 2/5 mr squared omega squared. So the 2's are going to cancel, and you're going to be left with 1/5 mr squared omega squared. And so from there, we have what the mass of the Earth is, and we have what the radius of the Earth. So now we just have to figure out what omega is. And so then we can get omega from a couple different things. So we know that the Earth spins around once in one day. So because our days are made from what, or how fast the Earth spins. That's what we based a day off of. So we're going to have one revolution for every 24 hours. And we know that 1 hour is going to be equal to 3,600 seconds. And so then we just have to say that we have 2 pi radians for every 1 revolution. And so then this will yield the value of omega for the Earth. And so then you just plug this into your K here, and that will yield you the kinetic energy of the Earth, or the rotational kinetic energy. And so then we have to say, okay, what is the rotational kinetic energy of the Earth due to its orbit around the Sun in joules? And so we use the same formula. And so from here, we will get the same formula here, but omega is going to be different. And so we have to use omega in a different way here. So omega for part 2 is going to be equal to, we're going to have 1 revolution around the Sun for 1 year. And so then we have to take that there's 1 year. For every 1 year, there's 365 days. And then for 1 day, there are 24 hours. And then for every hour, there's 3,600 seconds. And then once we've actually converted this, we just have to say that there's, and then there's 2 pi radians per 1 revolution. And then this will yield our omega. And then you plug this back into here, or into this equation here, and that will yield your answer for the kinetic energy due to the sun. Okay, hello. So next up, we're going to be talking about the parallel axis theorem again. But this time, we're going to have a uniform disk of radius r and mass 2m is pivoted at point P around a point mass of half m that is attached to the edge of the disk. So first of all, we have to calculate the moment of ICM without the point mass with respect to the central axis of the disk in terms of big M and big R. So first of all, ICM is just simply going to be 1/2 mr squared. This is just the eye of the disk. You can pull this formula from your book, and then we plug in what m is going to be, and so then that's going to be 2m r squared. And I guess we have to plug in what r actually is. And then this is just going to yield us with mr squared. Calculate the moment of inertia P of the disk without the point mass with respect to point P in terms of big M and big R. So now we have to use the parallel axis theorem, and we have to use the fact that IP is going to be equal to ICM plus m r squared. So we already have what ICM is, and that's going to be mr squared. And then we just have to plug in these additional terms, plug in the masses here. So this is going to be 2m r squared, so this is going to yield 3m big R squared. And then we have to calculate the total moment of inertia, IT, of the disk with the point mass with respect to the point P in terms of M and R. So then IT is going to be equal to IP plus I mass. And we're just using the parallel axis theorem again, and we plug in what we already know. We have 3mr squared, and I mass is going to be just mr squared as well. And so from here, we just have to start plugging in stuff. Oh, and this mass here is going to be 1/2 of the disk. So this is going to be little m r squared, right? And so then m here is going to be m over 2 times 2r squared plus 3m r squared. So then we're going to have to square this term, and this is going to yield us a 4 and an r squared. And so then the 4 is going to cancel with the 2 here. So we're just going to have another 2m r squared plus 3m r squared, and that's going to yield us 5mr squared. Simple as that. Okay, so now, next up, we have a pumpkin of mass m and radius r. The pumpkin has the shape of a sphere, but is not uniform inside, so you don't know its moment of inertia. In order to determine a moment of inertia, you decide to roll the pumpkin down an incline that makes an angle theta with the horizontal. The pumpkin starts from rest and rolls without slipping. When it has descended a vertical height of h, it has acquired a speed of v is equal to a quantity. And so we're going to have to use conservation of energy in order to find this moment of inertia here, because it's not a uniform one that we know of. Okay, so a couple things we know. We know that the energy at the top of the hill is going to be equal to the energy at the bottom of the hill. So at the initial height, this is just going to be mgh. And then at the bottom of the hill, it's going to have its translational energy and its rotational energy. So this energy is going to be split in half. So we have 1/2 m v squared plus 1/2 I omega squared. So one thing that we have to do is we have to get this all in terms of one variable here on this side, and we have a conversion factor, right, for v, right, where omega is just equal to v over r, and we know what v is because the problem gives it to us. It says it's the square root of 5/4 gh, which makes sense. Here. So we can go ahead and plug in these numbers here, and then this is going to come out very quickly, and then we just have to go ahead and do some simplification. So we're going to have m gh on this side still, and this is going to be equal to 1/2 m, and then v squared is going to be 5/4 gh, and then we have to have plus 1/2 I over r to convert this r squared, to convert this omega to v, and then we have v squared, which is going to be 5/4 gh. And so I'm going to collect some of these coefficients first and make sure that we have all our ducks in a row, but we can instantly see that the g's and the h's cancel out. That's one thing that immediately goes away. And so what we're going to have here is we're going to have these 1/2s, right? So this is going to be m alone on this side. And then we'll have, this is equal to 5/8 m plus 5/8 I over r squared. And so we can get the I all alone by itself. And so we'll do that. We'll have the mass of the pumpkin minus 5/8 m, and then we can multiply both sides by 8/5, and then we multiply both sides by r squared. And then that's going to yield us I. So let's simplify this just a tiny bit. We can factor out our m. We only need one of those. And let it sit next to our r squared. And then we can start combining some like terms here. So this is going to be 8/5 in here, because this is going to be times a 1, minus, and this is going to be a 1 here. which we can instantly put into 5 over 5. So it's going to equal our I. And so then this is going to be 3/5. So then I is going to be equal to 3/5 mr squared. There you go. There you have it. That should be your moment of inertia. Let's check our answer. It is. Okay, so we have a spherical snowball of mass m, radius r, starts from rest and rolls without slipping down a roof that makes an angle theta with the horizontal. And they ask us, what is the angular speed of the snowball after it has traveled the distance d down the slope? And they give you 4 different answers here. So let's sketch out this problem here. So I think we're going to have to start off in a similar way, except this time I think we're going to know what our I is going to be due to it being a sphere. And so then we'll go from there. And I believe that it's going to want it in terms of d sine theta instead of h. So we can convert for that and make up for that very quickly. Okay, so we have mgh, and we know, or we can easily say, a couple things. We can say that that if we analyze the hilltop here, that this is going to be h, this is going to be theta, and this is going to be the distance d that it rolls down the hill. And so then we have what h and theta are. So this is going to be our opposite. So we can say that d is equal to h, or we can say that h is equal to d sine theta. So we can replace our h's with that. And remember, this equation still applies here, but in this case, I for this sphere is going to be 2/5 mr squared. And so we just have to plug that in. I feel like this isn't picking up right. Two-fifths mr squared. And so from this, what we can do is we can start plugging these in everywhere that we see an h, and we can start solving here. Oh, and also remember that v is equal to omega r. Yeah, that's not working. Let me look for a better marker. Okay, so we can start plugging this stuff in. So we'll have mg d sine theta here. Okay, that's better. Right, smoother. And we'll have a couple things here, and we'll have this is equal to 1/2 m r squared omega squared plus 1/2 2/5 m r squared omega squared. We'll just make this a regular r. So we can see that right off the bat that the m's cancel, and you're just going to be left with g d sine theta is going to be equal to 1/2 r squared omega squared. The 2's here cancel out, and so this will be 1/5 r squared omega squared. And so from here, we can combine these two terms. We have to find a common factor, and I believe this one is going to be over 10. So this is going to be 5/10, and this will be 2/10. And so from here, we can say that this is equal to 7/10 r squared omega squared equals g d sine theta. And so then now we can solve for omega squared. So omega squared is going to be equal to 10 over 7 g d sine theta over r squared. So omega is going to be equal to 10 over 7 g d sine theta over r squared. Okay, and so what we have to do here is we have to say, next question up says a yo-yo is made of two uniform discs, each mass m and radius r, which are glued to a smaller central axle of negligible mass and radius 0.5 r. So a string is tightly wrapped around the axle. The yo-yo is then released from rest and allowed to drop downwards as the string unwinds without slipping from the central axle. Find a moment of inertia I of the yo-yo with respect to the axis through the common centers of the disk in terms of mass and radius. So a couple pointers for this. So first off, you're going to have two different disks here, which are both going to have a moment of inertia of 1/2 mr squared. Since there's two of them, you just add them up, and that'll give you your answer. And then next part asks you to calculate the linear velocity v in meters per second of the yo-yo after it has fallen a distance of 0.25 meters. So we can start to draw this one out, given that it moves translationally. So it starts from here, right? And then at this point, it has extended this 0.25 meters, or this height h. So at the beginning, it has mgh, potential energy, and at the end, it'll have 1/2 mv squared plus 1/2 I omega squared. And so we'll have to do this conservation of energy here. And so we can start to put this together. We know what I is from the first question. So we'll have that this is equal to 1/2 m r squared omega squared. And we know what v is because v is equal to, this is going to be 1/2 m r squared omega squared. And we can see that our m's are going to cancel. So on this side, we have mgh over here. Cancel those. And we're going to have gh is equal to r squared omega squared by just adding these up. And so then we'll just say that omega squared, or omega, is going to be equal to gh over r squared. And that should be reliant on your answer, because you're given what r is, and you're going to be given what g is, and that should yield what your omega is afterwards. Oh geez, okay, no, I've actually screwed up. So here in this case, we see that I went from one to another. So I replaced the wrong variable. We should keep this as v because we have what v is. And this is going to be omega is going to be equal to V over R. And so then this is going to be equal to V squared over R squared instead of the other way around. So then there's an R squared here, and this one cancels with this one. And so this is going to be equal to V squared is equal to GH. And from there, we can say that V is equal to G over H. And there's no 2 here. At least there shouldn't be, because we added up this side together, so these 1/2s add up to equal 1, and we canceled all our m's out. And so this should just yield this answer here. Okay, I'll be uploading this to YouTube, and I'll see you guys in the next one.